Louisiana State University, and the topic I'll be presenting today is the interface bond characterization of engineered cementitious composites (ECC) in pavement applications. ECC, also known as bendable concrete, is a novel type of hyperfiber reinforced cementitious composites that is characterized by its high ductility under uniaxial tension. This remarkable attribute is reflective in its flexural performance. In the first picture, we see an ECC beam under their point bending test. And in the second image, we see a flexural performance graph that compares three different cementitious materials. The first material is concrete, represented by the black dashed line. Concrete, after reaching its peak strength, loses its load carrying capacity without undergoing any deformation. The blue line represents fiber reinforced concrete that after reaching its peak strength loses part of its load carrying capacity while undergoing some deformation. Finally, the orange line represents ECC that after reaching its peak strength has an increase in its load carrying capacity while undergoing substantial deformation. The implications of ECC properties for the transportation industry are the following: significant thickness reduction compared to typical concrete for the same service life, potentially jointless concrete pavements, and a more resilient and durable transportation infrastructure. Even though ECC has remarkable attributes, it has some challenges related to it. It has a high initial cost due to the usage of expensive oil-coated polyvinyl alcohol fibers at 2% of volume fraction. It also utilizes microsilica sand, and it has a high cement content. It's relevant to say that both the microsilica sand and the PBA fibers are not readily available. At LSU, we developed a cost-effective version of our ECC material, and we named it with the code M3 1.5%. This material has 1.5% of bulk fraction for PBA fibers, and it uses fine river sand instead of microsilica sand, and finally, it has 75% of cement replacement with fly ash. In terms of the mechanical properties, the compressive strength of this cost-effective ECC version is 25% superior than conventional concrete. The flexural strength is 113% superior than conventional concrete. The tensile strength is 24% superior than conventional concrete. And finally, the tensile strength capacity is 280 times that of regular concrete. We decided to put this material up to the test, and we repaired a cracked concrete pavement at LSU. This pavement is located in front of the engineering building, and we have been monitoring it so far, and it hasn't shown any signs of distress. The next stage of our research is implementing ECC for Ultrathin whitetopping applications. But what's a whitetopping? A whitetopping is a rehabilitation solution for distressed asphalt pavements. Whitetoppings are divided in three main categories according to their thickness: conventional whitetopping with a thickness larger than 6 inches, thin whitetopping with a thickness that ranges between 4 and 6 inches, and ultra-thin whitetoppings with a thickness between 2 and 4 inches. Ultra-thin whitetoppings are typically made with concrete or fiber reinforced concrete with a joint spacing that ranges between 4 feet by 4 feet and 6 feet by 6 feet. The main characteristics of UTWs affecting performance are its reduced thickness, its small joint spacing, and the bond between the asphalt substrate and the cementitious material. Even though UTWs have shown satisfactory performance so far with traditional materials, several distresses have been associated to them, such as corner brace, reflective and thermal cracking, and longitudinal cracking. Now we want to study the bond characteristics of ECC and concrete with asphalt in order to see how that affects the performance. It's relevant to say that the bond between concrete and asphalt has been previously studied in the past. However, no studies have been performed on ECC AC bonding conditions. For this purpose, we built an ECC UTW in Port Allen, Louisiana last year. The UTW overlay layout is the following. We constructed 3 sections. The first section is a 2.5-inch thick ECC section with a length of 60 feet, followed by a transition of 5 feet. The second section is a 4-inch thick ECC section with a length of 55 feet. And finally, As a control, we have a 4-inch thick concrete section with a length of 60 feet. It's relevant to say that the ECC sections are completely jointless, while the concrete section has 4 feet by 4 feet joints. These sections will be tested in the future under accelerated loading to see which material performs better. As for the objectives of the present study, we want to investigate the bond characteristics of ECC and regular concrete on AC substrates through direct shear and pull-off tests. Our methodology was the following. We conducted a sand patch test by ACM E965 in order to characterize the macro texture of the asphalt. Then we took 6-inch cores from our milled and unmilled asphalt length. We poured ECC and concrete on top of this cores, and we conducted the Louisiana interlayer shear strain test by HTP 114. Then, in order to characterize the tensile bond strength, we took 2-inch cores throughout our UTW, and we performed the pull-off test by ASTM C1583. From these samples, we obtained more specimens and conducted microstructure characterization. In terms of the failure modes for UTWs, we have 2 main groups. Mode 1 for the tensile failure mode, and mode 2 for the shearing failure mode. Mode 1 is classified in 6 main failure types. Failure type 1, 2, and 3A are failures by adhesion that occurs at the interface between the cementitious material and the asphalt. Failure type 3B and 4 are failure by cohesion that occurs at the asphalt aggregate and in the asphalt binder respectively. Finally, we have failure type 5 that is not associated to any particular mechanism. However, it occurs due to the presence of voids at the interface. On the other hand, mode 2 by shearing can be classified in 3 main groups: adhesive, cohesive, and mixed failure type. In terms of the results, the sand patch test gives us the mean texture depth. And for the milled asphalt substrates, we obtain a value of 0.037 inches. However, for the unmilled asphalt substrate, we obtain 0.024 inches. It's relevant to say that these results complied with the acceptance criteria for macro texture according to DuPont and Baudin. In terms of the interlayer shear strength test results, the concrete sample on top of the milled asphalt substrate yielded as a result 164 psi, while the concrete on top of the unmilled asphalt substrate yielded as a result 117 psi. It's relevant to say that these results were larger than the values obtained from a previous experiment for characterizing the interlayer shear strength in UTWs conducted at the St. Louis Airport in Missouri. In terms of the interlayer shear strength results for ECC, for the specimens on top of milled asphalt substrate, the result was 111 psi, while for the specimens on top of an unmilled asphalt substrate, the result was 52 psi. The difference between the results for concrete on top of asphalt and ECC on top of asphalt is mainly attributed to the presence of aggregates inside the concrete composition that get in contact with the fracture surface of the asphalt, increasing the mechanical bond. Now, in terms of the specimens and the classification according to the failure type, it's relevant to say that the ECC AC specimens fail mainly adhesively. On the other hand, the concrete AC specimens fail in different manners, such as cohesively in the asphalt, adhesively at the interface, and mix failing the concrete samples and the asphalt specimen. Now, as for the pull-off test results, for the concrete section, for the 4-inch concrete section, we obtain 84 psi of the pull-off strength, which is categorized as poor according to the sprinkle and also the dream criterion. As for the ECC specimens, the pull-off strength could not be measured because they debond due to coring activities. In terms of the categorization for the specimens, ECC samples failed adhesively. However, only one sample, sample number 4, failed cohesively. This is relevant because it shows that even though low, there is some degree of attachment between ECC and asphalt. As for the 4-inch concrete AC cores, they failed mainly cohesively. As shown in the previous test, the interlayer shear strength test, and in the pull-off test, the bond between concrete and asphalt is superior than the one between ECC and asphalt. So in order to determine the situation, we conducted a scanning electron microscopy analysis in order to get more insight. The first two pictures represent the bond between asphalt and ECC. In the middle of the picture, you could see an interface, and if we zoom in, we could see an interlayer, which have a relatively big width of actually 88.8 microns. And next to this interlayer, we can see high presence of unreacted fly ash particles. Now, as for the concrete AC specimen, at the interface, this interlayer material could not be found, and unreacted particles were also not found. So we decided to conduct EDS analysis on these interlayers, and for the ECC AC specimen, we found a high carbon content up to 69% of the weight of the sample. Previous research has shown that this is an indicative of the presence of hydrocarbons and aromatics groups in the asphalt. So it is hypothesized that these compounds are consuming the CH crystals. Now, because ECC utilizes a high level of fly ash, we believe that the puzzolans present in the fly ash are not reacting due to the lack of CH crystals being consumed by the asphalt. In terms of the concrete asphalt interface, the largest compound found were calcium up to 36% of the sample weight, followed by carbon up to 28% of the sample weight. These values are indicative of the presence of hydration products and hydrocarbons. In contrast to the ECC, this concrete pavement only uses 25% of cement replacement with fly ash. Therefore, the governing reaction is cementitious, as such, producing hydration products with greater ease. Finally, our conclusions. The interlayer shear strength of ECC and concrete with AC depends significantly on the substrate texture. The interlayer shear strength of concrete AC specimens was greater than that of ECC AC specimens for both surface treatments, milled and unmilled. Yet differences were intensified for unmilled AC substrates. The concrete AC tensile bond strength quantified by a pull-off test was found to be poor. On the other hand, the tensile bond strength of ECC AC specimens was non-existent to very poor, such that coring activities could have caused debonding. SEM EDS analysis revealed a high presence of unreacted fly ash particles near the ECC AC interface, thus suggesting that fly ash exhibits difficulty reacting with CH crystals to form hydration products due to the presence of asphalt carbonic compounds. SEM EDS analysis performed at the concrete AC interface revealed high amounts of calcium, carbon, and oxygen. This was indicative of the presence of cement hydration products and hydrocarbons at the concrete AC interface. I would like to acknowledge the participation of the Transportation Consortium of South Central States, the Louisiana Transportation Research Center, and the Pavement Research Facility in this investigation. Thank you very much.